Welcome to the next video about getting started with open commissioning. In this video, we will show how to build a very simple but complete model for virtual commissioning from scratch using the open commissioning tools. So this, what we see here, is already the end result. So we have a very basic machine consisting of one drive that is controlled by a very simple control program using a NC task that is connected to a drive in an TwinCAT master. And in the same TwinCAT solution, we have the simulated machine using an TwinCAT simulation module and a control program for the behavior of the drive, which is built using the open commissioning tools. The kinematic behavior of the drive is then simulated and visualized in Unity with a model built with the open commissioning Unity package. So for building this model, you need to have TwinCAT installed with the open commissioning TwinCAT library. Then you need to have the open commissioning assistant application on your system and Unity with the open commissioning Unity package. How to install all those, you can check out the documentation of open commissioning. Another component that you need to install for this example is the open commissioning TwinCAT library for TwinCAT. You can find this in this repository. Go to releases, download the library, and then to install it, you open TwinCAT, go to PLC, library repository, go to install, select the library that you downloaded and install it, and then it is available in TwinCAT. We will start by modeling the 3D simulation and the visualization in Unity, and then we will continue creating the TwinCAT solution and modeling all the required components to control that. So let's get started with modeling the drive in Unity. So the starting point is a completely empty Unity project with open commissioning installed, and we have the CAD model of a linear unit that we got from the manufacturer. This unit consists of a motor, there's a coupling, there's the linear rail, and the slide on top of it, which moves when the motor is active. So the CAD data here consists at the moment only of meshes. So everything we can see here is a mesh that is rendered, and the structure is exactly like it was designed in the CAD system. So what we need to do now in the first step is to restructure the meshes to make it a little bit more clear and clean, but also to represent the kinematic structure of the unit. So in this case here, we basically only have one linear axis on which the slide here is moving, and the rest is basically static. So a good way of doing that is to create a completely new game object and fill it with the relevant meshes. So let's create an empty game object. Let's call it linear unit. Let's move it to 0, 0, 0 and begin creating the child objects that represent the structure. So in this case, as I said, we only have two main parts. One is the static geometry. Let's call it geometry. And the other one is the linear axis. So now we can begin moving the meshes into the game objects where they belong to. Let's first unpack the prefab for that so we can move the meshes out of it. and begin with the linear axis. So here we only have one mesh representing the slide, which is this one. So we can move it inside the game object for the linear axis. Let's hide that. So we can select every other mesh, which is static, and move that into the geometry object of our linear unit object. So we can see now every mesh is in the newly created game object. We can delete the old one, and we have way more clearer and cleaner structure for that unit. So now that we structured the CAT data, let's continue to add the open commissioning components that are required to model the actual movement. So the general concept is that a movement is defined by an axis component and controlled by an actor component. So let's begin by adding an axis component to the game object representing the linear axis. So here we define which movement the axis can perform. We have the type option here, translation, rotation, or virtual. In this case, translation is the correct one because we want to model the linear movement of the slide here. And the direction we have to set to the Z axis. So the blue one is set, the movement is in that direction, so we have to set it here. When the axis component is receiving a value from its actor component, it will move its game object according to that value. If it's rotation, if it's a rotation axis, it will rotate the game object. So now let's create the actor component for this axis, which is in this case position drive. So we can create a new game object. Let's call it MA01 and add the drive position component to it. So this component can receive a control value from TwinCAT, or we can also override it and provide a value manually. And this needs to be referenced in the linear axis component. So right now there is none, but if we drag and drop it in here, we see that now this axis component has a reference to the drive component as its actor. So you can think about it like that the axis component is defining like the possibility of a movement. It's defining the type and the direction, and the actual movement is controlled by the actor. So an axis by itself cannot move. It always needs an actor providing a target value. And since the target value provided by the position drive is in millimeters and the base unit in Unity is meter, we have to convert it by using the factor that gets multiplied to it. So we 001. So we convert the millimeters to meters that it will move accordingly. So now let's start the simulation. Go to the position drive component, override it with a value, for example 50, and we see that the linear axis has moved 50 millimeters. When we go to the component here, we see it got the target value, multiplied it by this factor. This is the result, and it moved the game object to that position in the Z direction. So when we go back to the drive, but it's in 0, it will move back. So we see that everything is modeled correctly for that axis. It is also possible that one actor component is referenced in multiple axes. For example, in this module here, behind that housing, we have the clutch, which connects the motor with the linear rail here. And we could also model the rotational movement of that axis here. So let's do that quickly. We just have to create a new game object in that position. Let's move it outside here, position it here. Let's call it rotation axis and fade it around. Now we have again move the meshes that belong to that axis into the object. So this would be that one, this one, that one, this one, and add again the axis component to it. This time the type is rotation axis around the Z axis. So the direction is Z, the type is rotation. The actor component again is the same drive, so we just drag the same object inside here. So both the rotation axis and the linear axis are controlled by the same actor component, the same drive. Because again, the target value of that drive is millimeters, and the rotation axis, of course, has the units in degrees. We have to factor that in using the factor here. The thread pitch of that unit is 12 millimeters per rotation. So per millimeter, it should rotate 30 degrees. So we have to set the factor to 30. So it is modeled correctly according to the mechanical connection here. Okay, so let's start the simulation again to see if everything is modeled correctly. Let's give a target value to 100. And we see the linear axis has moved the same as last time. And also the rotation was modeled here in that axis. So again, if we go back, we see the rotation is modeled correctly as well. Okay, so let's have a look at the overview of the system we are going to build now. So the general idea is that we have a regular TwinCAT PLC project here, where the control program is implemented, which is connected to an EtherCAT master, which contains the devices. So in this example, we only have one drive, but there could be another drive or many other devices. And this part here is basically no different from a PLC project for a real machine. So you would connect your EtherCAT master to the real devices, to the real machine, and can control them with the control program. But since we are doing virtual commissioning, we of course don't have real devices and the real machine, so we need to simulate them. And this is where the second part here is responsible for, and also where open commissioning comes into play. So in the control program, we only are using TwinCAT tools, whereas in the second part, the simulated machine and simulated devices, we are using TwinCAT tools and also the open commissioning tools. So the library of the behavior models, the assistant application, and also the Unity package for the physics simulation. So let's have a little closer look at the control program. It is implemented in a PLC project, and the program contains some code to control an axis using a regular TwinCAT NC task. So the axis in the NC task is mapped to the program and also mapped to the device representing the drive in the EtherCAT master. So it's a very basic program. We will use the NC task functions to commission the drive when it's running. The EtherCAT master object has an adapter assigned to it, which is physically connected to the adapter assigned to the EtherCAT simulation object. So at the machine that I'm working on, I connected this with a real Ethernet cable. And from here, we are entering the area of the simulated machine. So first we have the EtherCAT simulation, which contains the same devices as in the EtherCAT master of the control program and provides a counterpart for the EtherCAT master. So it handles the communication with it and also provides an interface to the inputs and outputs of the devices. These inputs and outputs are then linked to a global variable list in a second PLC project where they can be read and written by the behavior models of the devices. So this second PLC project is the platform for running the actual behavior models of the devices. When it's running, it is exchanging data with the field bus simulation using the global variable list. It's running the logic of the behavior models. In this case, it's the state machine for the CAN Open 402 drive control. And it's also exchanging data with the physics simulation running in Unity using the ADS connection. The PLC project for the behavior models itself and most of the components can be created automatically by the Open Commissioning Assistant application. So the global variable list for the EtherCAT simulation can be automatically generated when the assistant detects an EtherCAT simulation object in the project, and it detects the devices in that and links the relevant inputs and outputs to the global variable list. The behavior models for the devices can also be created by the Open Commissioning Assistant based on the project defined in the Unity simulation. We showed this in another video, and we will also see it later when we build this here in this video. So next I will show how to create this system from scratch. One thing to note there is that we're going to create both PLC projects in the same TwinCAT solution. So the control project and the PLC project for the behavior model will run in the same TwinCAT solution. This is technically not required. Actually, in most cases, those would run on two different PCs. So you would have one simulation PC running the behavior model project and the EtherCAT simulation, and one engineering PC for the control program running the control project and the EtherCAT master. And then both of them are connected via Ethernet. But for this video, I don't have two PCs available, and maybe you don't have them either. So I will show how to do this on one TwinCAT system running on one PC. So let's begin by creating the TwinCAT solution with the assistant application. Let's put that overview here so we can see it while we are creating it. So the solution is created and opened in TwinCAT. So we see the assistant created the whole solution and also the TwinCAT project called OC which will contain the behavior models of the devices. So we start now by creating the second PLC project for the control program. So let's add a new item. Let's call it control. And wait until it's finished. So after it's created, we have to add the references for the motor control library from TwinCAT. Add them. So we have them available for controlling the axis. Okay, so now we can start creating our little logic. I will speed this up probably. So I have a little axis function block here with a reference axis and MC power and MC move absolute blocks, which gets called in the main function. So we can use that to control the axis in the MC task. Okay, so this part is done. Let's create EtherCAT master with drive device next. Let's go to I/O, add new item, EtherCAT master, call it. And let's select the adapter to which the simulation will be connected to. Okay, so we created the EtherCAT master. Let's add now the drive device to it. Make system item. Go down to the motor you want to add. Click OK. And now we see that this drive has been added as a device. Let's rename it to MA_1. Next, let's add the NC task to the solution. So we will show the motion configuration, add a new item, NC task, and add an axis. And let's call that also MA_. And to link it to the PLC, we first have to build the solution. And then select the axis reference in our main program that we created here. So now we're basically done with the control program. We created the control PLC project with the logic to control one axis. We added the NC task, the EtherCAT master with the device, linked them all up. So now they're ready to go, and we can continue with creating the rest of the system. And we will start with the EtherCAT simulation. So let's go to I/O devices, add new item, select EtherCAT simulation, and select the adapter to which the EtherCAT simulation is connected to. So in this case, I will select the one that is connected with the cable to the adapter of the EtherCAT master. And let's rename it to EtherCAT simulation. So now we need to add the counterparts of the devices in the EtherCAT master to the EtherCAT simulation. And we can do that by exporting the EtherCAT configuration to a file. So we go to EtherCAT master, then EtherCAT and export configuration file. Let's name it master configuration. And then let's click on EtherCAT simulation, right click, import ENI file and select the exported XML. And we see it created the exact same device in the simulation that's in the master. So now we have access to the inputs and outputs of that device in the EtherCAT simulation. So now that we created the EtherCAT simulation and the device counterparts, we can now continue to generate the global variable list for the EtherCAT simulation. This takes the relevant inputs and outputs of the devices and makes them available in the global variable list for the control program for the behavior models. So when we open the assistant, it is still connected to the solution. And when we click project and update project, it will automatically recognize that there is an EtherCAT simulation object in the solution and create the global variable list based on that. So when we click update project, we see here, it created a new folder with the variable list for that EtherCAT simulation. So now the last thing we need to create is the behavior models for the devices. In this case, it's only one device, and the mapping between the behavior model and the variables in the global variable list of the EtherCAT simulation. So to generate the behavior model for the drive, you have to go back to Unity and add another component, which is the client component. So let's create a new game object. Let's call it project. Let's move the unit inside there and add the client component to it, which can trigger the assistant to update the TwinCAT project with the behavior models of the devices in the simulation. Okay, so let's do that. Let's move Unity here, the assistant here, so we can see everything. When we click Update TwinCAT project, it will trigger the assistant to create the behavior model of the devices inside the simulation in the open commissioning project. Before we start that, we have to change the behavior model that will be created for the drive. So when we go to the game object that contains the device component, in this case it's the drive position component, in the communication area, there's property type, which defines which behavior model is created for that device. The default model for drives is FB drive, but in this case, we want to use a different model that implements the state machine for the DS402 drive controller, which is called FB DS402. So now when we go back to the client component and click update TwinCAT project. It triggers the assistant. It says the update was successful. And when we look into the main function, we now see that for this device, for the drive, the behavior model was created. The last thing we need to do now is map the inputs and outputs of the behavior model to the variables in the variable list of the TwinCAT simulation. So we can do that in the init run of the main function by calling the assign address function of the behavior model, which maps the inputs and outputs of the behavior model to the corresponding variables in the GVL of the TwinCAT simulation. So in this case, control word gets mapped to the control word in the TwinCAT simulation, and status word gets mapped to the status word in the TwinCAT simulation. Okay, so let's activate the configuration, start the TwinCAT system, and see if everything works together. So we also need to start Unity and check auto connect in the client, so it automatically connects. So TwinCAT is started, the system, and we already see that Unity also connected to the ADS client, so that's good. When we now go to the axis in the NC task, in the online tab, we see that the status is not ready. For that, we have to quickly activate the controller feed forward and feed backward values in the main program. So let's go to the main program, log in, and force the values for enable positive and negative to true. Back to the axis, and now we see they're true and the controller is ready. So now when we press the forward and backwards buttons, we see the drive in the simulation is moving as expected. So forward and backward. So we see the whole communication between the main program, the NC task, to the TwinCAT drive, to the TwinCAT simulation, to the behavior model, to the Unity model is working. And we can use the same tools for commissioning the virtual drive as we are using for real devices. You can also use the function here, for example, reversing sequence. Then it will move from one position to another with a specified speed. You can see this is exactly modeling the movement that is controlled here. So this brings us to the end of the video. Thank you very much for watching.